We're going to look at 1996, number 3. This is part A. So in part A, they want to know what delta S is for the reaction, or they tell you what delta S is for the reaction, and they want you to calculate the standard molar entropy S of C2H6 gas. So what they're saying is there's a blank in the table up here, and we've got to figure it out. So this is a products minus reactants situation. So you can see the delta S is equal to the sum of the entropies of the products minus the reactants. And then when I plug that in, we know the delta S of the overall reaction. And we have products, so 1, so we're doing C2H6 here. 1 times, we don't know that value, that's what we're trying to find in the problem, minus the reactants, so 2 times 1.130, so this is the H2 gas that's being represented, and over here is how we do the C2H2. And from this point we just got to do the algebra and figure out the math. And when you do that, it comes out to be 229.6 joules per Kelvin mole. For part B, they would like us to calculate the delta G for the reaction and then say what the sign indicates about it. To do that, well, we already know some things. Definitely the equation we're going to need is delta G equals delta H minus T delta S. We already know delta S from the first part. It was 229.6 joules per Kelvin. Maybe right now I'm going to convert that to kilojoules. I'm going to put the decimal there and say kilojoules and kind of get rid of that guy. Because we know that delta S is the only one of the 3 that tends to be in joules. This value right there we know is going to be, I believe, 298. Let's see, calculate the value of the free energy. What does the sign indicate? Yeah, I'm going to go with 298K. They don't really specifically say. Maybe they made an error this year because I'm looking at the key, and the key says they accepted 298 or 273. So in any case, we know those 2 values. Obviously, the thing we're going to need to figure out is delta H here. So I'm going to take a moment and do products minus reactants. Alright, so here's the work. I'm just doing products minus reactants, and I'll show you what these indicate. Products is this, we're doing C2H6 here, so the coefficient in the balanced equation is 1 times its delta H. And then over here we're doing hydrogen, and of course its delta H of formation is 0. And then over here we're doing C2H2, and its balanced equation has a 1, and then its delta H of formation is 226. When we calculate it out, we get delta H of negative 311. That is going to go right up here, negative 311.4 kilojoules. And at this point we should be able to calculate it out. And when they do that, they find that the delta G turns out to be negative 242.1 kilojoules. So that's the final answer. The one thing it doesn't explain, though, which you would need to do at this point, is it says, what does that indicate about the above reaction? Well, it would be simply a matter of saying the delta G is negative, and therefore, because it's negative, the reaction proceeds far towards products. In part C, they want us to calculate the equilibrium constant. Well, you can easily relate the equilibrium constant to delta G, which we already know, using Gertlink. So we're going to plug in our value for delta G here, which was negative 242.1 kilojoules. We're going to be very careful because you remember that this R being 8.314 is in joules per mole Kelvin. But we can't have that. We can't have this in kilojoules and that in joules. So we're going to want to do 0.008314, yep, kilojoules per mole Kelvin. The temperature we're assuming is still going to be 298. And then we can solve for it. When you do solve for it, you're going to get to a point where you've moved all of this R and T, you divided it by both sides and put it over there, and you're going to have natural log of K equal to, it says 97.7, And then, of course, remember to get rid of this, you need to do the inverse natural log, which would be e to the 97.7. And that should give you the equilibrium constant. And the equilibrium constant turns out to be 3 times 10 to the 42nd. So extremely large equilibrium constant. This is a reaction that goes far towards the products, which we probably could have predicted by the size of this delta G. And then in part D, we are wanting to find the value of the carbon-carbon double bond energy. So it looks like we're moving over here to the bond enthalpy table, and we're trying to find this little question mark here. They have an unknown in their bond enthalpy table. And you remember the way we normally do this is we divide up the reaction into the side that is full of things that we need to break. We're going to break those bonds and we're going to make these. So we've got to write down what bonds there are. And you remember that one of the things you got to be cautious about is what the bonds really look like. In hydrogen, we're pretty sure it's just a hydrogen-hydrogen single bond, and there must be 2 of them. So we're going to do twice of 436, which is 872, I believe. And then we're going to do our C2H2, and that one we might want to draw out. So it's 2 carbons, there's 2 hydrogens, and I'm guessing they're spread out on either side. And then they've got to have 4 bonds to carbon, so it only has 2 so far. We can't add more hydrogens, so I think there's at least a double bond, but that only gets the carbon up to 3 bonds, so it might be a triple bond. So there's a triple bond in this one, so we are going to have a carbon-carbon triple bond, and a carbon-hydrogen single bond. You may have noticed that I stopped there. In my print, it looks like that's a double bond, but it must be a triple bond. Alright, so if that's a triple bond, and we know the CH single bond, we know that there are 2 of them per molecule, and there's only 1 molecule, so there's 2 of these. So our carbon-hydrogen single bond is 414, so twice that would be 828, and then we don't know this one. On the side where we're making the bonds and the energy is being returned, we probably need to know the structure of C2H6. So it's going to have 2 carbons and 6 hydrogens, and I think they're going to be spread out. I'm going to put 1 there, 1 there, and 1 there, and then 1 there, 1 there, and 1 there. And so you'll notice that already when we spread out the 6 hydrogens, each carbon has 4 bonds. So there are going to be no double bonds. So each molecule is 1, 2, 3, 4, 5, 6 CHs. So we have 6 CHs, and I wish I had left myself more room. But fortunately, oh, and then we got our carbon-carbons. So I'm going to put the 6 CHs down here. So it's going to be 6 times the 414 is going to give us 2,484 kilojoules. But then we also have to do the carbon-carbon single bond. There's only 1 of those, and that's going to be 347. So now I'm going to add up the 2 columns, and we'll put them in these 2 boxes. I'll add up this column and put the answer there, and add up this column and put the answer there. Alright, so there we go. We add up this column, we get 1700 plus x, and remember we're going to subtract these 2, that minus that. And all that should equal, and normally I'd write it on the right, but I don't have any more room, it should equal the delta H of the reaction. And so we got to go back up and figure out what we thought the delta H of the reaction was, and I'm looking it up right now. It was negative 311.4 kilojoules. Which we found out earlier when we were finding delta G. You remember in this step in part B, we learned what the delta H of the reaction was. So now all we have to do is solve for x. And when they solve for x, it looks like the answer is 820 kilojoules. When you do the test, though, you're not going to leave this as x. You're going to say that this is the bond enthalpy or bond energy, either one. You're going to label it of the carbon-carbon triple bond.